All right. Hi, everyone. So today we're very happy to have Julian Sonner to give us a talk about an ETH matrix model from JT plus matter. Thank you so much, Julian, for accepting to give this talk, and please go ahead.
So yes, thanks, Nima. Thanks everybody for coming and for inviting me to give this talk. So this is some recent work that I published with Dan Jaffress and David Kolchmeyer and Bauer Mohamed Sanov. And it started out with a very simple and I think appealing idea, but then, the paperwork got very serious very soon. And I just want to really say that both of the more junior members here, David and Bauer, have done really a titanic effort. And it's really thanks to their efforts that these results were possible. Right, so I will, however, I will give a general introduction, and depending on how that goes, feel free to ask questions. I can obviously be quite interactive also with this iPad setup. So the general idea is actually to talk about quantum chaos, and also to sort of smuggle the idea of topology into the way that we talk about quantum chaos, and to see what we can do there and what we can learn about gravity, and in particular quantum gravity. Of course, we'll be more specific. I will tell you about the kind of quantum chaos signatures that we're interested in. So here I'm just very generally denoting quantum chaos by some chaotic billiards, and we'll see here some chaotic trajectories. And also I will tell you more what the arena is of quantum gravity that we can talk about. But in particular, one preview is already going to be that certain very typically chaotic correlations will show up on this gravity side as wormholes, Euclidean wormholes in space-time. So therefore, this connection between sort of correlations of orbits, let's say of chaotic systems, and the idea of non-trivial topology in space-time. So the general motivation is that, well, there are several. I have written down three. Firstly, one way that one can motivate such work is that we've been for a long time interested in understanding the late time unitarization of black hole observables. So by this, I mean things like, perhaps the entanglement entropy of some subregion, or the entanglement entropy of the radiation, let's say, or simple two-point functions of fields that might propagate on the black hole background, and other things. Many of these things, when calculated from a theoretic classical gravity point of view, suffer pathologies that are seemingly not acceptable in a unitary quantum mechanical system. And this is one of the main motivations, is to find physical effects that help us understand the late time behavior of these observables and to reconcile them with the expectations of unitary many-body quantum systems. So in fewer words than that, we want to understand the black hole and the thermal physics associated to a black hole by thinking about quantum thermalization. And quantum thermalization immediately leads to the ideas of chaos, which I've already mentioned, and ergodicity, and all the beautiful associated phenomena. So the first motivation for thinking about chaos in this context is, again, specific physical principles that allow us to understand late-time unitarization of black hole observables. Second motivation, which comes when one is a little bit more familiar with the way that we think about many-body quantum chaos. And that second motivation is, actually, we would like to make progress on the spectrum of black hole microstates, or microstates in the theory of gravity. Meaning that, it is very nice that by now we have a pretty good handle, I think, on how to count the microstates. So to say something about the entropy of black holes, certainly within the context of string theory, and also more generally maybe in ADS-CFT, But what is still a great challenge is to ask dynamical questions, which notably actually depend on the exact spectrum of the theory. It's not just the number of microstates. We actually want to know what structure is in the microstates. What is the structure of gravitational microstates, in particular, high energy black hole microstates? And that's, of course, a very worthwhile problem. And it is, as you can, of course, already imagine, it's related also to this late time behavior that I already mentioned. But I also want to throw out the point here that that's a computation that is both challenging and very interesting, because the average separation of microstates in this regime, delta, will be of non-perturbative order in the entropy. And that's simply because, of course, the entropy of the black hole S is the area over 4 times g Newton, so it's finite. And so if it's finite, then we can say that there's going to be, in a unitary quantum system, a discrete number of microstates that there is e to the s of them, e to the s Bekenstein-Hawking, and therefore the average separation parametrically will be e to the minus s in the entropy. And so that's, we want to understand the very microscopic spectrum of black hole microstates. And it turns out that quantum chaos is actually a very nice physical principle that allows you to understand this kind of resolution, among the microstates. And then the final motivation, and that's the one which is probably closest related to the slice through these ideas that I want to give you today, in particular relationships to ETH, eigenstate thermalization, is that I think that a great deal of progress has been made on lower dimensional systems in recent years, along those lines, along the lines that I just sketched. But of course, one of the big questions is, what does any of this tell us about physical dimensions or higher dimensional setups? And so we would like to maybe see a way out conceptually how we can extrapolate general lessons in lower dimensions to higher dimensional setups. And again, I want to argue that thinking about sort of these quantum chaotic approaches is a very nice idea in this context, because quantum chaos actually has the property that in some sense, it gives us some universal insight about these questions that I mentioned above, with, of course, then the great possibility and the hope that they aren't just true in lower dimensions where they might be artifacts, but actually those features carry over to higher dimensions. All right, so that means that in general, we would like to understand the emergence of statistical physics, so black hole thermodynamics in gravity. And to be a little bit more specific, that means via ADS-CFT, so both in asymptotically anti-de Sitter gravitational setups, as well as in strongly correlated field theories, which are supposed to be dual to these anti-de Sitter gravity setups via the ADS-CFT duality. Right. So then maybe I should pause here and ask for questions about the motivations, because I will now go a little bit more into methods and results. But also, if you give me just 5 seconds, there's something that's making a noise here that's actually distracting me. 1 second. Excellent. I dealt with it. There was some ventilator going, sorry. All right, so has this interruption been enough for you to provoke questions?
Can I ask you a quick question, Julian?
Yeah, I asked for questions, of course.
So, are you going to comment on the potential connections between random matrix theory and ergodicity? Something that's confused me for a while now.
I haven't written this in this talk, but I can certainly try and make some comments. Yeah, I can try and make some comments.
Thank you.
Yep. Other questions?
I know this is a weird thing, but so you think the chaos is important, like an integrable theory will not have black holes or something?
I mean, that's a very good question. I think what one can say is that in principle, one would say that an integrable theory will not thermalize. And so if the thermal state corresponds to the black hole, then there is certainly something weird going on. But
so, we
however,
have
I don't think that
but...
means, I don't think it means that there isn't a black hole. But what it means is probably that it's not generically approached from a high energy initial state. You know, thermalization in integrable theories in some sense either doesn't happen or is more subtle, in the sense, for example, that you might thermalize to a generalized Gibbs ensemble. So those things might still occur. But what I do want to say is that there are certain properties in particular related not to black holes, but to these space-time wormholes. And those, I think, make sense when we talk about chaotic theories, and do not make so much sense when we talk about integrable theories. But again, we should come back to this discussion. I think it's an important question. I don't want to be so categorical as what you suggested, but I think that it makes sense, basically, the most sense to discuss these phenomena in chaotic theories.
Okay, thank you.
Okay. So so then let me say that the way that we want to think about the emergence of statistical physics is going to be via what I would claim is the modern approach to think about it, which comes from quantum statistical physics and also from condensed matter theory, which is on the one hand RMT, so random matrix theory, and on the other hand this thing called the Eigenstate Thermalization hypothesis, ETH. And I think that many of you are actually very familiar with this, but I will still go through some of the basics. So let me give you a brief reminder about the first, excuse me, about the first of these. So one often sees the statement that quantum chaos implies RMT, random matrix theory, in the following sense. This goes a little bit, by the way, in your direction, Nima, although I'm probably being still a little bit vague in this early phase. So what we want to ask, for example, a question that we want to ask, which is a sharp and useful question, is what about the spectrum of an individual physical theory, but one that is chaotic? So the statement is that such a system will have spectral statistics. So I will explain in a second in what sense we can define spectral statistics here, which approximate very accurately those that you get from just selecting your Hamiltonian at random and then averaging over a suitable set of random matrices H that you say are your random Hamiltonians. So one way to characterize this is we look at the frequency through the spectrum at which we find two adjacent energy levels at a particular distance. So I plot the distance from a level to its adjacent level, and I make a histogram. This is the gray thing here, a histogram, as I go through the spectrum. You see, and I will get something like this. I will get very few pairs of levels that are extremely close to each other, and then we'll get increasingly more levels that are further and further until this thing peaks, and it peaks actually exactly at this is bad notation now. Sorry, the difference in energy is this delta that are earlier. Delta is the mean difference, the average distance between them. So you're most likely to find them separated by their mean, but of course there are also gaps between eigenvalues which are much smaller or much bigger than the mean. But what is striking is that we compare this to the prediction that you get from asking the same question about adjacent energy levels in this random matrix distribution. That's what I have here in purple. And in a quantum chaotic system, in some sense, that's the definition of a quantum chaotic system. This histogram approximates extremely well this purple curve, the so-called Wigner-Surmites. So this is to say that the level statistics of an individual one quantum chaotic system is very well described by that of an ensemble of quantum systems, where the Hamiltonian is now drawn from an ensemble, and it's given by this specific curve. Two comments about this. One is...
So Julian, can I ask a quick question here?
Yeah.
When you say an individual physical theory, by that I understand you mean a typical age. You're comparing a typical age with an average age.
No, I literally mean,
Well,
for example, a chaotic billiard system, or I literally mean the Hamiltonian of...
for what values of the coefficients? Like, are you telling me that we cannot fine tune the coefficients to find a different spectrum?
No, you cannot. You cannot get a different spectrum unless you go to an integrable theory, in which case what you get would be a Poisson distribution. But let me address your question a little bit more again. I mean, there are two things that you should notice here. One is that I'm not asking about the exact spectrum. What I'm asking is about the correlation between two adjacent levels. So you can have, of course, different spectra, but on average, they have the same two-level correlation. Okay?
Yes.
Is that okay?
Yes. But I'm still...
So I'm not saying they all have the same spectrum, but what I'm saying is that, and that's the second comment, if you look at the distribution of two levels at the average, you look at the scale that is comparable to the average separation, then you will find almost perfectly this Wigner curve in quantum chaotic systems. You do.
So then, can I ask a quick question? If what you're saying is correct, you could replace that random, by random I imagine some hard random, some measure, with your favorite measure, and it should fit. There's nothing special about a uniform H. If all H follow this pattern, the measure is independent, is irrelevant. You could just put your favorite measure and integrate.
Yeah, this is actually the statement that at sufficiently small level of separations, that all of these quantum chaotic systems are actually given by the Gaussian, let's say, quality orthogonal ensemble. So if you just want to work in the universality class of random Hamiltonians, you could write some H that has a very complicated potential. The statement is that once you go into this region here, then all of them will start looking like the GOE. And then I can actually, I have some explanation why that is the case. Again, I have not included this in this talk, but maybe that would take me a little bit too far afield, but afterwards, if we have some time, I can comment on that.
For sure, thank you.
Yeah. Okay, so right. Excellent. Now, right, so that's that. And one thing that I can maybe remark, because some of you probably seen this, there is like a Fourier transformed version, roughly speaking, of this, where I think about time. Actually, people typically like to think about log time. They think about the log of, let's call it K of t. K of t is roughly the Fourier transform of P. It's not exactly the Fourier transform of P, but it's very related. And that's the thing that gives you this so-called spectral form factor. Okay, this spectral form factor is basically a real-time version of this. And the fact that at late enough times, I'm only showing the late time behavior. At late enough times, this will have a universal form which people in our community call ramp plateau behavior. Okay, that's the same story. And okay, fine, that's just a remark. Of course, I'm showing here only the average quantity. The real quantity will have fluctuations, but let's sweep that under the rug for a second.
So
that's what I want
here. Sorry, Julian. So would you say that the onset of the random matrix behavior, would you say is E times of order E2 power S?
No, it can be much earlier. So good. So the diagram that I showed here only shows you basically the universal part, but the time scale at which the physical system, like your billiard system or some other quantum chaotic system starts looking like a random matrix theory is actually usually called the Thouless time, T Thouless. And this Thouless time, it does not have to be parametrically e to the s. In fact, in many systems it isn't. So for example, we calculated this in SYK. In SYK, it's actually s to the 1/2 log s.
I see.
So much less than e to the s. So there's a very large time, parametrically large time, where this is a good approximation, even before you are at e to the s times. Okay. One feature that is reliably at e to the s time, since you asked that question, that's this sort of turn over here. This ramp plateau turnover, that's reliably at e to the s time.
I see.
Okay. Right. Good. So the second concept is ETH, the Eigenstate Thermalization hypothesis. And that's another way I want to emphasize that you can associate ensembles with individual quantum systems. So ETH is also supposed to be true only in systems that are quantum chaotic. And ETH is a very nice framework, conceptual framework that allows you to understand thermalization in such chaotic quantum systems, even under unitary evolution. Yes, for subsystems, basically. The way that it works is that it says that actually high energy microstates themselves are thermal. So the thermal values are actually encoded already in the eigenstates. So of course, I are the microstates of our Hamiltonian or of our system. And ETH is often presented, but I will want to present this in a different way just in a moment. But the way that it's usually presented is that we take some operator O, which is supposed to be small in some sense. It's supposed to be a probe. So for example, one could say it's a local operator or an operator that only talks to a small number of degrees of freedom that doesn't scale extensively with the size of the system. And the expectation value of such an operator O can be written as on the diagonal, you actually have exactly the microcanonical expectation value, really the thermal expectation value at the energy E, that's the average of the two eigenstate energies I and J. And then you have off-diagonal components, which again are actually modulated by a random matrix. R is a random matrix, much more about this in a few minutes. Then there is some smooth function of the energy, average energy E and the difference energy. So one could also have said that this depends on both of the energies, the I and J. And notably, it's suppressed by e to the minus s of E over 2, where s of E is the microcanonical energy. But what this is saying is that the thermal averaging is already hiding in individual microstates of individual quantum chaotic systems. And this can be shown in a few lines to imply thermalization of these local, or in some sense small observables on average. So for example, one has to do a little bit of time averaging to see the thermal behavior, but it's a very good way of understanding how individual quantum systems can behave thermally, even though, say, the global state of the system is pure. Okay, and so I've already said this, but I want to emphasize it one more time. Both RMT and ETH associate some notion of ensemble to individual systems. So there is a clear relation between one Hamiltonian and something like an ensemble of Hamiltonians in RMT, or let's say a thermal ensemble in the ETH sense. Okay, yeah, of course.
So the ETH statement is very quantitative, right? So it's pretty clear what we mean. Whereas the first RMT story you mentioned is qualitative, I'm understanding. Because you said that it looks like it, you didn't parameterize the error bars, right? How far does this histogram, what controls how close this histogram is to the RMT answer? Could that be made rigorous? Could the RMT thing be made rigorous? What error bars and everything controlled?
Yes, I think so. And what one would have in mind here is actually that you would sort of try and again take a scaling limit where here what we've been doing, we've defined this sampling in terms of some bin size. So we had to put like, a certain energy difference, and all of the levels that were within that energy difference, we put it in there. Okay. But we have to probably think about a limit where we can take the number of bin sizes to 0 while we scale effectively the number of eigenvalues that we keep to infinity, right? And then I think you should get some statement that basically the two-level correlation function will approach this Wigner surmise, and then there will be fluctuations on top of this, which will be quantified by higher moments, and that should exactly describe your energy level statistics, or if you want in real time, that should exactly describe this curve and its fluctuations on top, because those are the higher moments.
Thank you.
Yeah. Okay, so let's then go to the actual question that I would like to answer. The question, of course, that many of us would like to answer is, A, is this useful in gravity? And B, well, let's say, how is this realized in gravity? Maybe is the first question, and B, is it actually useful? So I'd like to tell you a little bit about how these things are realized in gravity, and then we can maybe together decide whether it's useful or not. Okay, so one prime example of a relation that will, in the first instance, be between gravity and random matrix theory is the celebrated connection between JT gravity. So this is Jacques-Teitelbaum gravity, for those who haven't heard, and a certain matrix model, which is so an integral over one random matrix that we call H, but it's a random matrix model, which is actually in a double-scaled sense. And of course, this is the beautiful work of SSS, Sarchenker, and Stanford. So JT gravity is a two-dimensional theory of gravity with this particular Lagrangian. So it looks almost like Einstein-Hilbert gravity, but it has this dilaton field. The statement is that if I look at so I should say that in 2 dimensions, I want to remind you that if I just take the Riemann Einstein-Hilbert term, the Ricci scalar, and I put something here in front, which we call S0, then this gives me actually just S0 times the Euler number of the manifold that I integrate over. That's, by the way, also the reason really why you want to include something like the dilaton field, so you get non-trivial dynamics. So the Euler number basically appears in this theory naturally as a coupling constant, and we can call the coupling constant formally S0 here in front for historical reasons. So then what has been shown is that all of the space-times, including higher topologies, which are taken into account by this thing here, this gives you an expansion in e to the minus S0. Okay, to some power n, which is given, as we said, by the Euler number. And you can have a one-to-one correspondence between this expansion, which is a non-perturbative expansion in gravity, and the perturbative expansion of this matrix model here. Meaning that every term you can calculate here. So for example, you can calculate the space-time that has like, 2 boundaries, and then has like a crazy kind of topology in the middle. This is in one correspondence with quantities that you can calculate here in this matrix model. And so the way that I like to think about it is that what these spacetimes here calculate are actually correlations between energy levels. For each boundary, you associate one energy level, rho E1, E2, and you get some gravitational prediction. And this should be related to correlations of energy levels. These are the chaotic energy correlations of this matrix model, of the SSS matrix model. Okay, so there is a correspondence between gravity and the matrix model at so far the perturbative level in the matrix model. But I just wanted to I wanted to advertise that in some sense, in recent work with Atlant, Post, van der Heyden, and Verlinde, we showed that in fact this whole thing can be made to work also fully non-perturbatively in the matrix model. And in order to make this work, I don't want to go into the details again, ask me afterwards if you want. We really had to dig deep into the quantum chaos technology. And we basically were able to show that there is some non-perturbative formulation of JT, which we call the Kodaira-Spencer theory of gravity. And this is really completely equivalent to the non-perturbative correlations, chaotic correlations that you can have in this spectrum well, basically these guys are already defined for us. So there is basically a fully doubly non-perturbative duality between gravity and quantum chaos. And the question that leads me to this ETH approach, which I want to tell you about, is whether something like this can ever work in higher dimensions. So could we really associate the space-time wormholes and the topology with those random matrix correlations that I have spent some time explaining to you? And what's interesting to me is that what turns out you need to do is you need to broaden a little bit your perspective, and you need to really start thinking about this ETH approach to quantum thermalization. And that's what with Daniel and with Bauer and with David, we set out to do. So,
question, Julian?
Yeah, of course.
I do not remember much about this Kodaira Spencer theory, but I recall it was a string theory. Is that right?
Yeah.
But I mean, the spectrum of such a theory would look very different from JT, right?
No, let me say a couple of words about this. So I need to get rid of my face here on the, okay. I mean, I need to get rid of the little window that has my face on it and blocks the, let me make some space here. So the idea is that JT is two-dimensional gravity, but we can actually realize this as the worldsheet gravity of a appropriate string theory. Okay, so in this formulation, basically a 2D universe, which might look like the one that I drew, let's say, has two boundaries again. So it has one boundary here and one boundary there, and maybe has one hole here. We want to think of this as the worldsheet of a string theory. Okay. And there's actually two ways of going there. One way is one that has been explored by Turiaci and by Mertens and by people around them, Blomert, I think, as well at some point. And that's, you can actually write down what's called the minimal string, the so-called PQ minimal string. Okay. In fact, you want to go to what's called the 2, Q minimal string. And you want to take the limit that Q goes to infinity. And that gives you JT gravity as the worldsheet theory of this string. But the second way that actually Eric Verlinde and friends and us pursued was you can actually also define JT as the worldsheet theory of the so-called B-model topological string. And that thing is basically going to be described by a spectral curve. And what we can do is we can feed into that spectral curve, we can feed the spectral density of JT, which is this sinh hyperbolic of 2 pi square root E. So what I'm trying to tell you, Nima, is that we can actually design a string theory, and other people can also do it. And they come to sort of equivalent results where they need to be equivalent. But the worldsheet of the string itself is the JT universe. So if we are the observer, we live on the world sheet. We don't live in target space.
Yeah, I guess you're saying that this is mathematically, if you identify the world sheet with space-time, it becomes the same type of string theory. Okay, I see. All right.
Yes. But then we can go beyond that, because this Kodaira-Spencer is actually the fully non-perturbative formulation of this string theory formulated in the target space. And this is, if you want, actually an auxiliary construction, except that what we did in this paper is that we put it into one-to-one correspondence with this chaos flavor matrix theory that Alex Altman and I had derived earlier. So now I gave you, like, in 10 minutes, unfortunately, what should be at least one lecture. I wanted to not talk about the solder work. I wanted to talk about the stuff with Daniel and Bauer and David. But I would be quite happy to tell you more about it also if there's time and questions. But yeah, okay, sorry. So back to where we were. So I just want to say, in some sense, that this is, to me, a very nice sort of example in which this mapping between chaotic correlations and space-time works extremely well. But it also is limited by the fact, I would admit, that it happens in low dimensions. And so I think we want to embark on the road to higher dimensions, and that there are actually quite a few interesting things that are going on there, also in 3 dimensions. But the first modest step that I want to talk about today, for the remainder of my time here in the seminar, I would like to say that one way of going to higher dimensions is actually we can stay in lower dimensions, but make them look like add degrees of freedom. For example, if I had a high dimensional theory and I would Kaluza-Klein reduce it down to lower dimensions, what I would get is I would get the gravitational theory plus a bunch of scalar fields. And so the first way of asking them the question of abstracting that setup is, let's take JT and let's add an actual scalar matter field to it, which we can take just to be a minimally coupled scalar field, where, of course, this scalar field phi in the ADS-CFT sense should be thought to be dual to some operator O with the conformal dimension delta that is determined by its mass. And where we just note that my hand-drawn var phi here is not the same as the dilaton phi that I had to have in the JT gravity as sort of part of the definition of what is gravity in 2 dimensions. So we add another degree of freedom. And now let me just give you the idea. The idea is that we take, again, a look at this ETH ansatz, which we already discussed. So here it is again. I've written this function f now in terms of the 2 energies EI and EJ. And we say that the way that is usually defined as ETH ansatz is that this Rij is supposed to be a random matrix, one that has 0 mean and that has unit variance. Okay, so unit variance, why? Because the variance does change as you go through the spectrum, but that's basically what this function f here does for you. So what remains, the random part, is really just a unit variance random matrix. And now comes a very simple intuitive idea, which is that we already know that we can think about the JT type part as a random matrix. This is this H type random matrix. And we want to think about this guy here up to some smooth functions also as a random matrix. So can we actually write a matrix model, which is now not a 1 matrix model, which we had previously, but a matrix 2 matrix model, which in the same sense will describe for us the physics of JT plus matter. And it turns out that it can be done. And it turns out that it has, in my opinion at least, the nice feature that it formalizes also the eigenstate thermalization hypothesis in terms of matrix models, which is not something that had previously been appreciated. So the plan of the remainder, maybe 15, 20 minutes, I said I will go back to some statistical physics type discussion, and I will argue for you that we really need to extend the way that that people usually introduce ETH, okay, I will then show that this extended notion of ETH is very naturally formulated in terms of a two-matrix model or multi-matrix model. And then at the end, I will show you that we can apply this again to the original problem, namely JT plus matter. But I do want to emphasize again that this structure here, 1 and 2, is something that is of independent interest. The application to ADS-CFT or JT plus matter is just one of what I hope are sort of many applications that the structure can have. Okay. So yeah, so let's go and extend the eigenstate thermalization hypothesis. So let's think about the fact that we have followed the convention. We have basically defined Rij as a Gaussian distributed random matrix. Okay, so the claim is that this is actually not correct. It's usually said that Rij is a Gaussian random matrix, but this can vary for some very basic reasons. This cannot be true because we'll get immediately contradictions. So the first set of contradictions is something that we noticed some years ago with my then graduate student Manuel Vielma, and that was also independently noticed by Fouini and Korchan and by Murthy and Srednicki, who worked on, who are mostly interested in statistical physics. And what we did actually is we tried to calculate, we tried to see, can you say something about these out of time order endpoint correlation functions? So by that I mean correlation functions of the type where you take, I don't know, operators that are like O of t, O of 0, O of t, O of 0. And actually, if you want, you can take many of those sequences. So by the way, typically people write them AB, AB. They want to have two operators here. But the feature is that you go forward in time, you go backward in time, and you go forward in time, and you might have many of these sequences. So these are kind of strange correlation functions, but they are interesting because they capture some features about the quantum chaotic nature of the system. And what you realize is that if you calculate such OTOCs and you assume the Gaussian ETH, you find that they are always trivial in the sense that they just factorize into two-point functions. But all of the interesting physics of these functions lies in the part that doesn't factorize into two-point functions, which is completely absent in the Gaussian approximation of ETH. And so in order that basically the ETH answers be consistent with known results on how these OTOCs behave, so this is something that we pointed out here, you have to have that there are non-trivial connected non-Gaussian correlations between these R matrices. Sorry, I'm going back here. Okay. There is a second thing, which I don't want to go into too much detail now because I'm already a little bit behind time, but we explained this in our more recent paper with Dan and David and Bauer. You even get wrong thermal mean field theory if you try to derive it from ETH, unless you include these non-Gaussian corrections. And these non-Gaussian corrections, they basically are of the form that so basically that 4 of these O's, so you should think of this as being like 4 of these R's, except that I'm implicitly rescaling them by the smooth functions, the sort of F-type functions that are here. Okay, so this whole object now, you could call this OIJ by some abuse of notation. Okay, I'm afraid this is a bit of abuse of notation, but that's what I'm going to do. So I'm going to call these kind of objects here OIJ. So they include the smooth function and they include the random matrix part. So for the OTOC 4-point function, you conclude that you must have a non-trivial connected contribution, which is given by now not e to the minus s over 2 as we had in the original ansatz, but it has to be suppressed by e to the minus 3s And then there's some smooth function that depends on all four energies, EI, EJ, EK, and EL. And this thing here basically contains the information about the OTOC. OTOC lives here. Okay. So actually, you can make a more general statement. You can show that actually, in order to be consistent with these higher order OTOCs and higher order correlations in thermal mean field theory, the ETH must actually contain non-Gaussian connected contributions, which are suppressed in general with power e to the minus n minus 1 s of e, where I have connected correlations between n operators. Okay, so the 4-point function is e to the minus 4 minus 1, so e to the minus 3s. And if you calculate correlation functions such as the OTOCs in the energy eigenbases, even though they are highly suppressed seemingly, they actually contribute at leading order to observables. And the reason is, of course, that there are many sums over the Hilbert space that come in correlation functions which compensate exactly for the suppression. So the suppression is in fact exactly designed to compensate for these additional sums over the Hilbert space.
Sorry, can I ask you
So
a question?
this,
I'm a little bit lost. I'm familiar with the paper that Shrednicki and collaborator wrote that where they claim that ETH does give you the bound on chaos, the chaos bound, right? So the ETH tells you that the OTOC will fall off exponentially, and the coefficient of that is bounded by follows the chaos bound. You're not referring to that work when you cite it. You're talking about.
I am, because actually, if you look at in that work, what they refer to as ETH is the hierarchy of these kind of non-Gaussianities, which was written down previously by Fouini and Korchan. And in particular, they talk about precisely this G4, and they actually give some general bounds for this behavior of this G4 and put that into relation to the OTOC bound. So that's precisely what's happening. You're talking about this paper by Murthy and Shrednicki.
Yes. Oh, okay. Maybe we can discuss this offline because I'm confused about that paper actually. Yeah. Okay. Thank you.
Yeah. Of course, there are some other comments to be made which we can discuss. But what I'm certain about is that when they say we use ETH to bound the OTOC, what they actually mean is they use this what I call generalized ETH in the form that was written down by Fouini and Korchan, and they of course they cite them.
Okay. Thank you.
Okay. Right, so this structure with Manuel we called extended ETH, but it has in the meantime also has received the name generalized ETH. So basically that there is a hierarchy of non-vanishing connected correlations between these matrices that one might have called Rij, but that I have rescaled and I call Oj. Second step. This structure, this hierarchy of correlations is very naturally written as a two-matrix model. So what the ETH gives you is sort of these Oj correlations, or these extended ETH gives you these Oj correlations. But what we're actually interested in are correlation functions. And correlation functions, you get to these correlation functions by summing over the Hilbert space. So for example, you might calculate some thermal trace, then you sum with e to the minus beta h, but you also have all these intermediate sums over the Hilbert space. And of course, by just defining your spectral density to be the sum of delta functions at all of the eigenvalues, eigenenergies, you can transform these spectral sums and correlation functions into integrals where you have inserted n number of spectral densities for n operators that you're summing. But now notice that this kind of thing here is precisely the natural structure that you get in a two-matrix model, which I will define for you now. So we'll define the ETH matrix model, which has some measure for the two matrices, H and O, which is some single trace potential V of H and O, where I define, and you will see in a second why I do this, the part that gives me the measure for H, I define it as the product of the integral over all eigenvalues. I have some non-trivial potential that I can put in here for the eigenvalues, e to the minus v of ei. And then I also have here the van der Monde determinant, where I'm not committing to what beta is, because that depends on the specific universality class that we want to be in. So 1, 2, or 4. And from this extended ETH, we learn that the O part of this potential, so I will illustrate in a second why this is the right choice, that the O part of the potential is basically given as an expansion in powers of the O matrix, where the coupling constant of each power is a function that I call Gn. So that's going to be O to the n with some suitable index contraction and some smooth function of the energy eigenvalues E1 up to n, where in fact those capital Gn's are related to the little Gn's that I had earlier. So these are basically the vertices that generate those correlations. But yes, sorry, there was a question.
The measure mu of H and O, you're assuming it to factorize, so it's mu of H times mu of O.
What I've done here is I've written it in the energy eigenbasis, the measure for H, right?
Yeah, but
in this case,
yeah,
it factorizes. But I think if you so there I have basically chosen a basis in which I've done a unitary rotation so that H is diagonal, and then I specify in that basis the O potential, and there it does actually factorize. But in general, I would say if I now go into a general basis again, where both H and O are non-diagonal matrices, I would say that the measure does not factorize. Yeah.
okay, thanks.
Thanks. So, right. And so basically those GNs are a set of unspecified smooth functions of the energy arguments in the same way that that they appeared in ETH. So this is now a general framework for a general chaotic system. But if we want to apply it to a specific quantum chaotic system, then we need to go further and we need to define a principle that defines these GNs. But for the time being, I'm working at the level of the general structure, just like ETH is the general structure. And of course, going to be able to specify what these G's are specifically is usually very difficult. And it's thanks to indeed some very hard work by my collaborators that in the JT plus matter case, we were able to do it. And I would ideally like to give you a sketch how, but that will be at the end. But for now, I hope that you don't mind that I leave them general. In fact, I think that's a feature. Just like in ETH, it was a feature that these functions on the diagonal and the off-diagonal functions were unspecified, and you could still get a strong statements about thermalizations, and even as Nima explained to us as well, even bounds on things like the OTOC. So at the level of this ETH matrix model, then I just want to say that there's a lot to explore, like what you can do with it. What you can do, for example, about bounds on things like OTOCs or correlation functions. What can you say something about this issue between ensemble and factorization that everybody is quite keen to talk about in gravity and so on and so forth? But actually, I do want to apologize because I thought that I said a little bit more about the measure. So let me do it now by hand. So the reason why this is the right choice of the measure is that you see, if you take something like this d mu of H, and you have any function here that depends on a number of eigenvalues, let's call it EK, then what this does is that, if this doesn't depend on all of the eigenvalues that H has, which has, let's say, n eigenvalues, then you can, of course, marginalize over all the eigenvalues that don't appear in this function. And what will remain is precisely the eigenvalue correlation rho, so of E1 up to EK with the product over the D EIs here at the end. That's what this measure will produce for you. And then at leading order in the matrix model, this rho will factorize into rho of E1 up to rho of EK. Okay, so the point is that if you integrate, so the point I want to make is that if we want to integrate with this measure, d mu of h that I defined, against any smooth function of energy eigenvalues E1 up to EK, you precisely produce an integral over the spectral density. You marginalize over all the energy eigenvalues that don't appear, and you get precisely the kind of integral that I wrote here. Okay, this just technically works, and so therefore it's the right choice. Okay, so let's spend maybe, I guess, 10 minutes. Maybe I can take 10 minutes.
Sure.
Yeah, on the rest. But actually, since I don't want to rush too much, I think I started a little late. So I also want to say, are there questions? Because I'm going to now really switch gears and go again back to gravity. So this is maybe a natural time to ask questions about this extended ETH and how we formulated it as a matrix model. Okay, great. So either it's all completely clear or I've basically been talking nonsense. So right, so we have this way of thinking about ETH and an extended way of ETH in terms of a two matrix model, where maybe I can make this remark now. I also have it at the end. The fact that it's a two matrix model, of course, corresponds to the fact that we've been looking at just one operator. And if you add more operators, then this becomes a multi-matrix model. So now let's go back to gravity and let's see what this buys us in gravity. So there is now the task is to see if we can use this to write down a matrix model description of JT plus matter. So let's remind ourselves again what happened, or maybe conceptualize a little bit more what happened also in this case of the one matrix model. So the one matrix model I integrate over this one matrix H with a potential. And in ADS-CFT, or in this JT matrix model duality, there is actually a sense in which we can think of this H as the boundary Hamiltonian. And because of this quantum chaotic context that I told you before, we could even think of this as standing in. This is the ensemble average that you get from one single quantum chaotic boundary theory. So think as an example, one instance of SYK at the spectral edge. But there is a second perspective on this, which is actually a perspective that is much older. People have been thinking about matrix models in two-dimensional gravity for much longer than this JT story. They never would have thought of this as the Hamiltonian of some quantum chaotic system, but they had another very nice perspective. And that perspective, I want to bring it in now to give you a little bit more intuition. That perspective is that you can actually use this matrix in order to define, in the first instance, a discrete triangulation of your space-time. So you actually keep this matrix finite, H as a finite matrix, and you look at its double-line 't Hooft expansion. And what you notice is that at least at the level of topology, you can associate like a two-dimensional space-time topology to this by just doing the usual 't Hooft counting. So we would start with the disk, the trivial topology, and we would add higher topologies, for example, disk with handle and so on. And if you were to calculate the density of states, the density of states is actually the average in this matrix model with a one boundary, fixed boundary. And we would basically calculate the disk density, which is what we call the trivial topology, and then there would be higher topological corrections. But this doesn't yet look very much like a two-dimensional gravity. So what you need to do to get a two-dimensional gravity is you take what's called a double scaling limit, in which you take then the size of the matrix to infinity. So that's n, the size of the matrix to infinity, while at the same time tuning to a critical point of this potential, such that you get a proliferation of vertices and you end up with this basically a smooth approximation to the geometry. So what one does is one takes this critical limit to the critical point, at the same time the number of eigenvalues to infinity in such a way that a certain ratio of n over g minus the critical coupling to some critical exponent remains finite. And in the JT case, we know that we need to identify this this with the coupling that I called e to the S0 earlier. S0 times whatever the Euler number is the power of the coupling. And actually how this is done specifically for a particular matrix model that in the double scale limit gives JT, even in the one matrix model, that's something that is, for example, part of this paper with Dan and David and Bauer. But that's just the one matrix thing. So what we really want to do is we want to include in this matrix model the second matrix, which we call the O lines. And so what you can calculate now is not just things like energy density and energy density correlations, right? We could have also calculated things here like rho of E1 up to rho of En. And that would have been instead a geometry that has n boundaries. This one only has one. But what we want to do is we want to go further. We want to also include O's. So we also want to have like sources for O at the boundary. And moreover, we need to include all of the O double lines as well. Okay, so how do we do this? So the idea is that we start with this ETH matrix model, and we choose these functions Gn to match the classical gravity at the disk level. Oops. Okay, so we basically take results that are known about JT in the semi-classical limit, and we match it to our matrix model at the disk level. But note that we need to make sure that the matrix model matches those JT quantities in a suitable double scale limit, because before you take double scale limit, you never match to a smooth gravitational theory. So, and then from the disk data, the matrix model gives you all the higher topological contributions. And that is something which, well, we would like to identify with some version of topological recursion for two matrix models. But that's maybe a comment only to the experts on this. Now that's still all words. So in practice, how do we do this? Well, in practice, the first step is that we take JT gravity, which has been written in a very nice form using some very elegant Feynman rules that comes first from a paper of Hermann Velinde and collaborators, and also Micha Berkuse and collaborators. And we deform them in such a way that we get finite versions. So the spectral density, which used to be supported on a half infinite line, this was the Sinch function that I wrote for you. This becomes a Q deformed spectral density, which has finite support, such that if I take the limit that the finite support becomes infinite again, I recover my JT. And furthermore, the vertices in this JT Feynman expansion, which were given by the 6 J symbols, they can also be Q-deformed in the same way, so that they give us Q-deformed versions of the Feynman rules of JT gravity. We then can design the G functions such that the matrix model recovers those Q-deformed rules and define a suitable double scale limit such that in the double scaling limit, it reproduces the actual gravitational answers. And the double scaling for us works in the way that we had this Q parameter here, which is the Q deformation of these 6 J symbols and the Q deformation of the spectral density. And we scale D, the size of the matrix, to infinity. I called it N earlier. We called it D now to distinguish from the general case. And then we scale Q back to 1. And then there is some function that is essentially the ratio of D over 1 minus Q squared times some function that is finite in the Q goes to 1 limit. We call that e to the S0. Well, as I said, we still need to work rather hard to actually determine what the matrix potential is. But we actually found 2 different approaches to this. One is sort of, if you want brute force, we can just iteratively determine it by making sure that all the Schwinger-Dyson equations of the matrix model match all the Schwinger-Dyson equations of the Q-deformed version of the JT gravity. Or in a more conceptual approach, we actually identified a particular constraint that has to be satisfied by this operator O in the JT gravity theory, and we can write this constraint as a constraint on the matrix. And then what we do is we basically identify this constraint in the matrix model by exponentiating it, which gives us actually the matrix model potential directly. And then once we have this matrix model, this potential in hand, we basically show that it reproduces the correlation functions of JT plus scalar, including the ones on higher topology. So here's an example, JT plus matter on the double trumpet, and we matched it exactly to the matrix model prediction. So let me go then to discussion in Outlook. Well, this is a technical comment, which I did not get into sufficient detail to really bang on about it, but there's basically different ways to regulate the matrix model. I only really talked about the Q regulator, but there was a second regulator, the Selberg regulator, and they actually differ on higher topologies. And it will be quite interesting to understand this better and what these theories really mean. Another puzzling feature is that the theory actually is sick. The JT plus matter theory is sick in the sense that there is a UV divergence when, for example, in this wormhole geometry, the length of the wormhole becomes too small. This is actually captured in our matrix model, and we can map it to an instability of the saddle point approximation of the matrix model. So at least around this saddle, that is the only one that I described in my talk, this matrix model itself has some UV problems, and we should therefore think of it more like an effective matrix model, which of course in our quantum chaotic approach is quite natural. But there is actually intriguingly the possibility that one could try and follow this instability in the matrix model and see where it goes and expand the matrix model around the new saddle point, around the new minimum, and see whether that actually allows us then to use that matrix model to cure that UV problem of the gravitational theory. What I want to say furthermore is that if you add more matter fields, I've already said, instead you get a multi-matrix model, which has recently been pointed out again by our friends in Paris, is related to what they call the theory of free probability. This comment maybe is the one that I want to spend most time on. So this matrix model approach, again, embedded into this general picture that it gives an effective description of quantum chaotic theories, that definitely applies in higher dimensions. So this ETH matrix model itself is a general framework that holds the promise that it can also apply to higher dimensional examples. But there, what would we actually do in order to tie down the theory? So I think that the most promising approach would be, in fact, to generalize this constraint construction. And for example, let's say that a natural target would be to write down an ETH type matrix model or 2D CFTs. In this case, what you would do is you would probably want to take some of the constraints that the CFT has to satisfy, such as, for example, the crossing constraint, and incorporate that in the matrix model. And that means that you would now want to write a matrix model that is the matrix model of the operator dimensions, that's like the energy eigenvalues, and the OPE coefficients, which satisfy a particular constraint. And the OPE coefficients, of course, are not matrices, but random tensors. So you would write something very similar, but not a multi-matrix model, but a model that has random matrices and random tensors, and that incorporates these crossing constraints of the CFT in an analogous way. And finally, okay, so let me not comment on Krylov complexity or anything like that. I would just like to say that there is sort of like a lot of ongoing work, some of which we are involved in, which I think kind of reevaluates the relationship between matrix models, generally quantum statistical physics, chaotic physics, and quantum gravity. And well, that I'm quite excited about. And I think I gave you just a little bit of an overview, that one insight. But okay, I'll end here and open for questions. Thanks very much.
For the great talk. Are there any questions? More questions for Julian? Well, we had plenty of questions during the talk, so
maybe I can ask. No, you said something about the Krylov complexity. Can you say briefly what do you want to do there, or?
Well, I mean, what necessarily not what I want to do, but it has already happened. So I mean, I have been, of course, interested in Krylov complexity myself, but not yet use this matrix model. But other people have pointed out that you can use this matrix model to find something like the late time behavior of Krylov complexity. And so whenever you try and calculate late time behavior of quantities now in two-dimensional gravity, and in particular two-dimensional gravity plus matter, I mean, this matrix model is basically, I think, a shortcut to get there. And so one thing that would be nice would be to maybe try and understand universal features of Krylov complexity at late times that are related to quantum chaos. And I believe that the right framework to do it would be such a two-matrix model.
Thank you.
Any last questions for Julian? If not, let's thank Julian again for the great talk. Thank you so much. This was wonderful.
Well, thanks for your patience.
No, this was
Julian.
Yeah.
Thank
you.
Thank you so much. All right, I'll send you the video, and we will decide. Thanks so much, Julian. Bye.
Bye-bye.
Bye.